The title of our talk today is Model-Based Certification of Cohesive Joints, and I will give this presentation together with my colleague Gerhard Oettel. My part is to first introduce you to a general framework for model-based certification and how we can support such a framework on the 3D Experience platform. And then in the second half of the talk, Gerhard will take over and guide you through a more specific example on cohesive joints that we have built using the simulation technology that our solver Abacus provides you with. We have structured our presentation accordingly. After a brief introduction, I would like to spend a few minutes on the 3D Experience platform and explain you how the platform can help to efficiently use simulation for driving the product development and how it can help to connect all related simulation data to the context the simulation was created for. Connecting or linking simulation data to the product development process finally means that we establish the digital thread. We ensure traceability of simulation data, so traceability back to its inputs and back to the context the simulation was created for. Talking about this aspect is quite important because traceability of simulation data is one of the key elements for assuring simulation credibility. And simulation credibility, on the other hand, is what you need to assure in order to get the approval from authorities for using simulation in a certification context. This means to do model-based certification, which is the main topic of our talk today. And then once I introduce this general framework, we will show you how the framework can be applied to an example of cohesive joints. So for the introduction, I would like to show only one slide, basically to introduce the scope of technology that we have to deal with when we talk about model-based certification. I am part of the SIMULIA brand of Dassault Systèmes, and in SIMULIA, our core competency is the simulation technology that we are developing, whether it is Abacus is our structure solver, PowerFlow for fluids, CST Studio Suite for electromagnetics, SIMPAC for multi-body simulation, or Wave 6 for vibroacoustics. But as soon as we talk about model-based certification, it is not only about the simulation technology itself, as you can guess from my initial remarks. It is also about managing simulation data. So data that is generated by the simulations, as well as data that is required as input for building the simulations. And this is why we have to talk about the 3D Experience platform as the place where we are connecting our simulation technology with technology offered by our sister brands in Dassault Systèmes. And most importantly, I have to note our sister brand Innovia, because Innovia provides a general data model for PLM objects, as well as solutions for lifecycle management of such objects. For example, managing versions and maturity states of objects, or controlling the ownership of objects. So in that sense, Innovia delivers the data management foundation of the 3D Experience platform. And of course, I also have to mention CATIA, our brand, as you certainly know, that offers a solution for 3D design. The geometry created with CATIA applications on the 3D Experience platform is usually a critical input for building simulation models, and therefore has to be closely linked to the simulation data. So in conclusion, the 3D Experience platform is the place where we connect our simulation solutions not only with the design environment, but much more generally with all processes that need to be established in the context of product development. And that's why I would like to start our presentation with a few more details on what this means and how this approach, so the approach of bringing all these technologies together on the 3D Experience platform, can help with driving the entire product development much more consistently through simulations. If In the past, you've listened to other presentations from my colleagues, either in SIMULIA or in CATIA. You may have already seen this slide, and I'm pretty sure you've also already heard the term ModSim before. But in case you have not, let me at least spend a few minutes on introducing what ModSim means, because in particular, the extended meaning of ModSim is quite important in the context that we want to speak about today. So ModSim is basically the term that we use when referring to our solutions for unifying modeling and simulation activities on the 3D Experience platform. So what does this mean more precisely? The traditional approach for building simulation models, that's what you see on the left-hand side, what I'm sure you are pretty familiar with, is that you first export CAD data from your CAD tool, then import the CAD file into your preprocessor, and do the defeaturing, meshing, etc. there. But the problem with this approach is due to the import-export process, you lose the link to your design data. Meaning, when the simulation results require that the design must be changed and that the designer has to update the CAD data, each and every step in this entire process has to be repeated more or less manually. Of course, this is time consuming and also error prone. In contrast to this traditional approach, we have unified all those steps in a consistent environment on the 3D Experience platform. On the 3D Experience platform, designers and simulation engineers can work concurrently on their data, while links between design data and simulation models are always preserved. So this means that data can easily be synchronized between the design world and the simulation world at any time and in both directions. So there's no more need for an error-prone import-export process. So with these capabilities, ModSim already offers a huge potential for time saving. Let's have a quick look at a very simple example just to show you how this works in principle. The example, here we are. The example refers to a frame of a fuselage structure. The designer has built a parametric CATIA model and a finite element mesh exists already. Now on the design side, meaning with the CATIA application, a design change is applied. To be more precise, the width of the flange is increased. And since the finite element model is fully associated with the CATIA model, the only thing you need to do in order to get the finite element model updated is to push the global update button. Because through such a global update, the finite element model will be automatically synchronized with the latest design data. Of course, this is only a very simple example to show the principle. Real-world models with large, complex assemblies certainly pose a number of additional challenges. But since the focus of today's presentation is a bit different one, I do not have time to talk about this aspect of ModSim in more depth. However, what I at least would like to mention with this regard is that this capability to automatically synchronize simulation models with design changes is of particular interest in the context of optimization tasks or general design studies. So whenever you're working on the topic of design exploration. And because we also provide a more or less complete set of both parametric and non-parametric optimization techniques on the 3D Experience platform, it is very efficient and straightforward to run such design and optimization studies based on these ModSim capabilities. But what is more critical with regard to the topic of our presentation today are those aspects of ModSim that closely link the world of design and simulation to the entire product development process. And this link is established through a number of data management processes, such as requirements management, change management, test management, and a few others. So requirements management, for example, is important because it allows you to digitally capture those requirements coming from the certification regulations. And talking about certification, usually you have to prove that an airframe structure complies with the certification requirements through test. Most of the time, such tests are real physical tests, but they could also be virtual tests, meaning could be simulations. In any case, what is important is that the test data, whether it comes from virtual or it comes from real tests, is linked to the requirements the test is supposed to verify. And this link between requirements and virtual or real test data, or in other words, the traceability from simulation data back to the certification context, can be achieved with the test management capability on the 3D Experience platform. And once we get to our example of cohesive joints, I will also show you how creating this link with test management actually looks like. But before we get to the example, I would like to talk a bit about how such a close link between simulations and higher level data management processes can actually help in the context of certification. So here on this slide, you see a traditional product development process represented by a V-cycle model. On the left-hand side, you see the different phases of design from initial concept studies to detailed design. On the right-hand side, then there are the phases of ramping up the manufacturing, building first prototypes, up to certification of the product. In a classical development process, simulation is primarily used on the left-hand side of the V. So in particular, in the context of designing or optimizing the product, the aircraft, for example. On the other hand, when looking at the right side of the V, the verification of certification requirements is predominantly provided through real physical tests that, of course, are causing significant costs to the program. So the objective should be to increase the use of simulations and at the same time reduce the number of physical tests in the context of verifying certification requirements. But of course, to do so, you have to build already fairly early in the program, prior to any certification activities, high confidence in both your simulation models and your simulation methodology. This means you have to work towards building simulation credibility, and you have to document how you do this. Confidence in simulation models is achieved if you can prove at any time that the models were built with the right inputs. And this requirement can be fulfilled through the close and direct link between design data and simulation models that we provide on the 3D Experience platform. I just showed a simple example how this close link can look like. And thanks to this link, we know at any time to which design revision a certain simulation model belongs. So in this way, you can at least assure confidence in simulation models. Meaning what is left is still the question how we can assure that already during the design phase, the required confidence also in the accuracy of the simulation methodology is achieved. And in this context, I would like to refer to the respective standards on verification and validation that are issued by the ASME, the American Society of Mechanical Engineers. And by the way, also the EASA, the European Union Aviation Safety Agency, has issued fairly recently in 2020 a memorandum with very similar content that summarizes requirements for assuring simulation credibility. So in particular, the ASME standard VNV10 requires that based on in the aerospace industry well-known analysis and test pyramid a systematic comparison of test and simulation results is carried out. So on the lowest level of the pyramid, on the coupon level, this comparison is typically used for calibrating material properties. And then on the higher levels, successively more complex structural components are analyzed to assure that also other model parameters, for example, the mesh refinement or the applied solution procedure, are chosen in a suitable manner. And if in this way you've finally demonstrated that the chosen approach for modeling and simulation is an accurate representation of the real world problem you're dealing with, then authorities may accept that the final proof of compliance with the certification requirements is based on simulation. So if you want to follow these V&V standards, the first step for you is to define a test strategy that is appropriate for the real world problem at hand, and that covers both all real physical tests and all virtual tests or simulations. Then in the second step, you have to validate the simulation methodology. This means you have to conduct the respective calibration and validation tests on the lower levels of the pyramid. And the final step consists of the top level certification test that may be conducted virtually with simulations, thanks to the validation activities that have been done at the lower levels. Okay, that's basically all I wanted to share about this general framework for model-based certification. Let's now move on and spend the remaining time of this presentation on the example that we've promised to talk about in the title of our presentation, which is cohesive joints. So for time reasons, we will not be able to talk about the entire process that I introduced on the previous slide, but we will definitely guide you through the main aspects of the first two steps. So defining a test strategy and then subsequently running calibration and validation tests. Let's start with the first step and see how you can digitally capture certification specifications on the 3D Experience platform by using requirements management, and then create links to such requirements when defining an appropriate test strategy. So on our internal 3D Experience server, we have digitized the entire CS25 regulation of the EASA, which is the certification specification for large aeroplanes. Practically speaking, this means that for every requirement from the regulation, we have created a PLM object on the platform that, for instance, can be linked to any simulation that is used for verifying the requirement. Another advantage is that treating such requirements as PLM objects means that you can assign them PLM attributes such as version number or maturity state. The bigger certification context that we want to use to look at our example of cohesive joints, these are the requirements on structural integrity of the airframe in case of an emergency landing. These are the requirements that you see on the screen right now. So they are documented in section 25.562 of CS25. Okay, let me pause the video for a second because I want to make a few more remarks before we get into the test management. Yeah, as I said, the top level certification test that we are interested in our example is a barrel drop test of a fuselage section that represents the emergency landing scenario. And assuming that we have to deal with the composite structure, there are a number of different failure modes that need to be taken into account because each of these failure modes has a strong influence on the energy absorption in such a crash scenario. And one of these failure modes, and that's actually the one that we want to focus on today, is progressive damage of the cohesive interface layer between skin and stiffeners. So for this example of a barrel drop test, and with particular focus on the failure of cohesive joints, we have now used the test management application on the 3DEXPERIENCE platform. That's what you see in the video right now, to define and capture a test strategy based on a pyramid of virtual and real tests. So here it's important to note that as part of the test specification, that's what you see here, a link to the respective requirement object is made. And so now for our specific example, when defining the test strategy, we have to consider that there are a number of different levels. Of course, we have the drop test itself. This is defined at level L1, but then we also go down to level L5, which captures all coupon level tests. These coupon level tests are basically needed for characterizing material properties. And of course, each level can also contain several tests, either virtual ones or real ones. And all of these tests that are defined as part of the strategy are represented by so-called test objects. So these are these individual items that you see in the tree here on the left-hand side of the test management application. And it's actually these test case objects which are linked to both the requirements and the simulation data from the virtual tests. So in this way, it is finally the test management application that ensures traceability from certification requirements to all related simulation data. Yes, so that's what I wanted to show you with respect to planning all of the tests, defining the respective test strategy. And now the next step would be to get a bit more into detail and look at the actual execution of calibration and validation tests. And at this point, I would like to hand the presentation over to my colleague Gerhard. At this point, I will also stop my screen sharing so that Gerhard can take over and has the full control on his own screen. So Gerhard.
Okay, so I hope you can hear me well and see my screen now.
No, we can hear you, but I think we cannot yet see your screen.
We can't see the screen.
Okay, yeah. Now
Yeah.
I see it.
You can see?
Yeah,
okay.
We can see.
Okay, so right after talking about the V&V strategy and planning, we will now switch gears a little bit and focus on calibration and validation tests. So at the coupon level, which is the bottommost level of our test pyramid, both physical and virtual tests are performed side by side. The test manager role on the 3DEXPERIENCE platform contains apps allowing to link the necessary requirements and the items on a test, allowed to describe all required steps for the physical test to be performed in the lab in a test script, and also eventually to gather the results of the experiment. The goal of the virtual tests at the coupon level is to calibrate the virtual material models that represent the coupon. So based on the physical or experimental results from the lab test, we are able to launch a calibration procedure aiming to accurately replicate the physical behavior of the coupon with our finite element model. And similar to a hardware lab test, any virtual test may also be planned and managed via the test manager role, and the finite element model of the coupon can be attached directly for further use here by the material calibration expert, for instance. At the validation level, which is level 1 of our test pyramid, the calibrated material models from level 0 can then be reused to virtually simulate parts or small assemblies and correlate these against corresponding hardware physical tests. Now let's dive a little more into detail and talk about the tasks at the coupon level first. So what we see on the right-hand side, typical finite element models which may be used at the coupon level. These can, for instance, be dog-bone specimen for replicating tensile tests, such as the one shown in the upper right figure. And such tests are very well suited for calibrating elastic plastic material behavior for metals, for instance. At the bottom right-hand side, we see a double cantilever beam model, which can be used to calibrate the traction separation behavior of adhesive materials. The picture on the left shows a glimpse of the SIMULIA material calibration app on the 3DEXPERIENCE platform. This app is particularly well suited for performing different material calibration tasks required at the coupon level. So as we can see in the red box, a broad range of Abaqus material models are supported for calibration, not only different types of elastic plastic or hyperelastic models, but also more sophisticated models like the parallel rheological framework model, the two-layer viscoplasticity, nitinol, or even user-defined material models. And for adhesive materials, the app supports cohesive traction separation behavior. The green box indicates 3 different execution modes offered by the material calibration app, which are used in the calibration procedure to compute the material's response. Of course, not all material calibration tasks require the use of full-blown finite element models, such as the one shown on the right. So depending on the material model to be calibrated, the app also offers the numerical and analytical execution modes, which run much faster than the finite element model-based calibrations. The analytical and the numerical modes access the material model equations or the Abaqus standard material library directly, which makes these modes extremely fast. On the other hand, the FA-based mode offers the greatest range of applications with respect to model and material response complexity, since it is based on a complete finite element models. Most important in this case is, of course, that any finite element model which is used in a calibration procedure runs very fast and stable. The material calibration app is very intuitive and easy to use, yet a very powerful tool at the same time. In most calibration cases, the user just needs to follow the icons shown in the calibration setup dialog here from left to right in order to set up and run the calibration. So the order of the icons may be also considered as kind of an assistant, which the user can simply follow step by step. And we will see such a calibration workflow in some more detail in a couple of minutes. The basic workflow for calibrating a material model consists of 3 steps as shown on this page here. First, we start with importing a set of test data. Several different formats are supported here for import, like Microsoft Excel files, CSV files, or ASCII text files. On import, the proper units for the imported quantities can be selected, and even time or temperature information can be added if necessary. For importing several sets of similar test data, it's pretty convenient that most of the user settings are kept from a previous import action. Since test data are not always nice and smooth and calibration against such data might be difficult, the app also offers a set of tools to edit, to repair, to regularize, decimate, or smooth the imported test data. Second, we need to select a suitable material model like elastic plastic or hyperelastic or hyperfoam, etc., or as in our case, cohesive traction separation. The list of the supported material models was shown on the previous page, and this list basically is also getting longer and longer with every release of the material calibration app. Finally, we can then execute the calibration and review the results. So while the calibration is running, the user also gets a pretty good idea on the progress of the optimization procedure, because first of all, the material response plotted together with the test data is constantly updated. Second, the calibrated material properties change accordingly. And finally, also the objective value is plotted against the number of calibration runs. So the 3 steps which we show here are sufficient for many kinds of test data and material model calibrations. Compared to this previously shown basic workflow, the FA-based calibration, which we are going to use for the cohesive properties, requires a few extra steps highlighted in the blue boxes of this diagram here. First, we need to import a run-ready finite element model. This can be a 3D experience simulation model or a native Abacus input file. One of the materials defined in this model has to be selected for calibration, and of course of utmost importance is that this finite element model runs fast and very stable, as I mentioned before. Furthermore, we need to define mapping between a set of test data and a history output of the finite element model. These two will then be compared against each other during the calibration procedure. And finally, third blue box here, it's always a good practice to perform an evaluation run before executing the full calibration. This evaluation run is a single solve of the model to prove that the calibration is set up properly and to show that the initial material properties produce a simulation response in the right ballpark. So as an example of a coupon level task, we will now focus on the calibration of our adhesive material behavior. In Abacus, basically, adhesive materials can be modeled either via a surface-based cohesive behavior included in a contact definition, or by means of cohesive elements with attraction separation material behavior. And as we have already seen in one of the previous pages, the material calibration app supports the calibration of traction separation cohesive behavior. So in what follows, we will mesh the adhesive material with a single layer of cohesive elements and assign cohesive traction separation material behavior to these elements. For both the formation modes, for the normal mode and for the shear mode, the material properties to characterize traction separation type cohesive behavior are the elastic stiffness, a certain damage initiation, stress or strain, and also the critical fracture energy. And furthermore, a certain mode mix law has to be selected, which quantifies the relative proportions of normal and shear deformation in the cohesive zone. Different types of mixed mode behavior are available, either energy-based or traction-based. The figure on the bottom left here is a schematic representation of the dependence of damage initiation and evolution on the mode mix for traction separation response with isotropic shear behavior. So the figure shows the traction on the vertical axis and the magnitudes of normal and shear separations along the 2 horizontal axes. The unshaded triangles here in the 2 vertical coordinate planes represent the response under pure normal and pure shear deformation, respectively, and all intermediate vertical planes that contain the vertical axis represent the damage response under mixed mode conditions with different mode mixes. On the right-hand side, then we see how these material properties are offered for calibration in the material calibration app once this cohesive traction separation behavior is selected. We see orthotropic traction type elasticity for the elastic stiffness values in the upper part of the dialog. In the middle, we note that a quadratic stress type damage initiation criterion was chosen, and in the bottom part of the dialog, the energy-based damage evolution and a BK type mixed mode behavior are shown. The damage initiation and evolution properties in the red boxes, with the blue check mark box activated, these are the properties which are selected for calibration based on existing experimental data. And these material properties will be modified in the course of the calibration procedure in order for the material response to best replicate the selected set of test data. If the elastic stiffness is already known, for instance, from the adhesive manufacturer, then the user can enter these known values and deselect the elastic stiffness for the calibration procedure so that the optimization algorithm will not be able to change the known stiffness values. As we see here in the upper part of the dialog, the elastic stiffness values do not have the blue checkmark box activated, so the calibration procedure will not change the user specified values here. According to ASTM standards, typical types of hardware tests used for investigating adhesive behavior are double cantilever beam tests and mixed mode bending tests. And the two simulation models shown on this page replicate exactly these types of hardware tests. The double cantilever beam on the left is used under pure mode 1 type loading, so it allows to calibrate the cohesive material properties related to pure mode 1 type loading, which are so the elastic stiffness in normal direction and the damage properties in normal direction. The mixed mode bending model on the right hand side is used for determining the mixed mode 1 and mode 2 fracture toughness, and depending on the length of the lever arm for the force, different mode mix ratios can be investigated using this model. Remember that the mode mix ratio is defined as the energy release rate of mode 2 over the total energy release rate. Now let's watch a short video demonstrating such a calibration exercise. The video starts by showing that an MOC4 laboratory test has been completed. It's a mixed mode bending test with a certain mode mix ratio of 0.2. The item under test is a mixed mode bending test coupon, and all the required test steps are documented in detail in the test script. The physical test results have then been attached via the test results capture app of the test manager role, and the status of this test is set to passed. The next step is the execution of an MOC2 test, which is a simulation, and in our case, it is the calibration of adhesive material properties based on a mixed mode bending test. The mixed mode bending simulation model is now opened here in the SIMULIA mechanical scenario app. I'll pause the video for a second. The layer of cohesive element is placed between the two plates. The mesh in the region of the crack front is properly defined here, and rigid cylinders and a frame structure of a model with connector elements are used to apply the mixed mode loading in a structural analysis case. So as you can see here, the model has been run with some preliminary cohesive material properties, and it is capable of reproducing a behavior similar also to the hardware experiment. So, and now the material calibration engineer can go ahead and use this model as a starting point, combine it with experimental results from our MOC4 test, and set up a calibration procedure for determining the cohesive material properties. And the main steps of such a calibration are shown next. So first, FA-based calibration mode is selected since we want to use the previously shown finite element model for the calibration. Then the experimental data are imported into the material calibration app as force versus displacement data in our case, obtained from the performed MOC4 test. Then the FA simulation model used for the calibration has to be selected. together also with the material to be calibrated, which is one of the materials available in this simulation model, the adhesive here. Next, the cohesive traction separation model is selected, and some damage initiation and damage evolution options are chosen here. And then before running the full calibration, it's always a good advice to perform a single run evaluation on the initial guess parameters. And if this initial solution is then in the right ballpark, then we can go ahead and launch the full calibration run. In this case, it's eventually not only one single finite element model which was used for calibration, but several different ones. Double cantilever beam model for calibrating the pure mode 1 related parameters, and several mixed mode bending models with different mode mix ratios. And once the calibration is completed, then we can export the calibration results to a 3D experience material object, which then can be reused for other simulation and validation models. So this latter process is also summarized on this page here. First, on the left here, we capture the calibration result in a material object on 3D experience. And for this, the material calibration app offers the option to create a material once the calibration procedure is completed and the user is satisfied with calibration results, which means that the simulation model produces a response sufficiently close to the experimental data. By means of the test manager role, the calibration results may be then reviewed, and the calibration test MOC2 will then be approved for completion. The maturity state of the material object can be changed from an in-work status to a released status. And finally, on the right-hand side, the released material model with the calibrated cohesive material properties can then be reused and applied to higher level virtual test models, such as the skin stringer validation model shown on the right-hand side here. Finally, now let's watch in a little video how the calibrated cohesive material model is then reused in a level 1 model or a validation level model. And the level 1 model under consideration here is a skin stringer assembly. Both the green-colored skin and the gray-colored stringer are composite parts. A rigid connection between these two parts is in place at both outer ends of the stringer, highlighted in white here. In the center, an initially debonded blue region is flanked by two regions of cohesive elements, and the initially debonded region can expand into these red areas as cohesive elements fail due to the applied loading. The video then shows how a composite layup is created with a certain stacking sequence of layers shown currently. And this layup is then assigned to the skin part by defining a composite shell section, as we see here, which connects the skin geometry and the defined layup. And a similar procedure is also required for the composite stringer. For the stringer, the flange and the web can potentially have different composite layups. As a next step, the cohesive property is defined for the two patches of cohesive elements, which you see here. Cohesive material created in the previous calibration exercise can now be reused and assigned to these cohesive elements. And then a cohesive property requires some additional parameters which are specified now in the video. Finally, the simulation scenario is defined, where the skin stringer assembly is subject to a shear loading into the post-buckling range. And we also see the test rig here modeled with a frame structure of I-beams and the loading which is applied at the two opposite corners of this frame. The simulation results first show here an animation of the out-of-plane displacements increasing with increasing load level. and a similar buckling pattern is also observed in our hardware experiment. And finally, we observed that the damage and failure of the cohesive elements take place starting from the initially debonded region in the center of the skin stringer connection and expanding outwards, as we see here in the video. So this brings me to the conclusions. In the presentation, we showed how the SIMULIA material calibration app on the 3D Experience platform allows to calibrate advanced nonlinear Abaqus material models for cohesive joints. However, also a broad range of other material models not discussed here can be calibrated, from elastic plastic models to hyperelasticity to even user materials. And at the coupon level of our test pyramid, this app can be very helpful for material calibration engineers to create material models for finite element simulation based on experimental test data. Furthermore, the 3D Experience platform enables the users to manage the life cycle and the maturity state of material properties, and it ensures full traceability all the way from the calibration source data of the hardware experiment to the final material model properties. Calibrated material models can then be reused with confidence in the validation level simulation models of the test pyramid in order to correlate simulations of parts or small assemblies to corresponding hardware tests. For this, we have presented a small skin stringer assembly as a level 1 validation model, where the traction separation cohesive material from level 0 calibration was reused. And finally, the test manager role on 3D Experience allows to define and manage a virtual plus real test strategy in order to support a model-based certification approach built on material calibration and the correlation of simulation models and hardware experiments at several levels of the test pyramid. Thank you for your attention.
Okay, thanks everyone.